Hi guys, we're on page 228, section 3.9, differentials, okay? There are several different concepts that we're going to cover in this particular section. The first three are on this page. The linear approximation formula is y equals f of c plus f prime c times the quantity x minus c, which is really the calculus way of writing y minus y1 is equal to m times x minus x1. Okay, that's just the calculus way of writing the point slope equation. Now, the idea behind a linear approximation is that you get an equation for a line tangent to a curve, and when you get that, you're able to use that linear equation to estimate values around that value of x, as long as the difference between x and the value you are, say, approximating is very small. So if that value right here is c, I'm trying to write it, sorry. If that value right there in the middle dotted line is c, this point here and this point here need to be very close to c in order for a linear approximation to be accurate. Okay, then the next thing we are going to do is find differentials and the change in y. A differential is represented by dy, that means the differential of y, and delta y is the change in y. Okay, that's the delta is that little triangle. Both of these represent a change in y. The differential method is a little less accurate than the change in y. The differential equation uses the derivative, and you can see this is your differential equation right here using f prime, which is a derivative, whereas the change in y does not use the derivative. Okay, so we'll go through how to use those three. The first example says to find the tangent line approximation of f of x is equal to 1 plus sine of x at the point 0, 1. Okay, 0 is our x, and because we don't have a y value, we are just going to be using the x. So our linear approximation, our L of x, which is the same thing as y, is equal to f of 0 plus f prime of 0 times x minus 0. So because we see the f prime, that means that we need to find the derivative of 1 plus sine of x. So f prime x is cosine of x. Okay, now we can fill out our linear approximation equation. F of 0 means that we are going to plug 0 in to 1 plus sine of x to get 1 plus sine of 0. Well, sine of 0 is 0, so 1 plus sine of 0 means that f of 0 is equal to 1. Now, f prime 0, when you plug a 0 into cosine of x, cosine of 0 is 1, and then we're multiplying that by x minus 0. So y equals 1 plus x minus 0, or y is equal to 1 plus x. And you can use that linear approximation to evaluate values of x that are very, very close to 0. Down at the bottom of page 228, they use the linear approximation y equals 1 plus x to evaluate x values of negative 0.5, negative 0.1, negative 0.01, then positive 0.01, positive 0.1, and positive 0.5. And if you look at the table, the f of x and the y are pretty close, okay? F of x equals 1 plus sine x has a value of 0.521 at negative 0.5, where the linear approximation equation has a value of 0.5, okay? And if you look at the tables, all the values in both of the y lines, f of x and y equals, are both very close. F of x is a little bit more accurate, okay? So this would be your tangent line approximation. Not the same thing as the tangent line to the function 1 plus sine of x. Okay? Now, example 2, we are comparing differential dy and delta y, which is the change in y. So our differential equation, dy is equal to f prime x times dx. Okay, well, if we have f prime x, that means that we need the derivative of y. So f prime x is equal to 2x. So the differential, remember, the differential always includes the derivative, okay? So f prime of 1 means that we are multiplying 2 times 1 times dx, which is 0.01. So 2 times 0.01 gives us a value of 0.02. Okay, now we're going to use the same information, but this time we're going to find delta y, the change in y, without using the derivative. Okay, so f of x is 1, delta x is 0.01, and then minus f of x, which is 1. So when we calculate the change in y, we are looking at f of 1.01. Well, f is x squared. So 1.01 squared minus 1 squared. So what we did was evaluated. So here's what we got. F of x is equal to x squared. We evaluated f of 1.01, which is where we got 1.01 squared. Then we evaluated f of 1, which is where we got 1 squared. Okay, so delta y is equal to 1.01 quantity squared minus 1. So delta y equals 1.01 squared is 1.0201 minus 1. So delta y is equal to 0.0201. So you can see how close the differential evaluation is to the change in y. Okay? The change in y, again, is more accurate because it's got 2 more decimal places to it. So the change in y is a little bit more accurate. Okay, Now what we're going to do is move on to the error propagation in example 3. This uses the change in y equation. Okay, so f of x, see here it is right here, f of x plus delta x minus f of x is equal to delta y. That is the exact same equation that we use for error propagation. So the problem says the radius of a ball bearing is measured to be 0.7 inches. So the radius is 0.7, and the measurement is correct to within 0.01 inches. So delta R is 0.01 plus or minus either way. Estimate the propagated error in the volume V of the ball bearing. So there is the volume of a sphere, because a ball bearing is a little itty bitty tiny metal ball, and I think they use them in tires and I don't know what else. Anyway, okay, so what we're going to do is find the derivative with respect to the radius. Okay, dv dr 4/3 pi, remember those are constants, times 3r squared. Okay, now we're going to solve for dv, the change in volume, by multiplying over the dr, because dv represents the propagated error in the volume, the change in the volume when your radius changes by 0.01 either way. Okay, now the 3's will very nicely cancel out, and we are left with the formula 4 pi r squared dr. Now dr is the change in the radius, which is also the same thing as delta r. Okay, so dv is equal to 4 pi times 0.7 squared times 0.01. And that gives us, it is, let's work on the calculator part of this. So 0.7 squared times 0.01 times 4 times, and I'm using my pi button, okay? And that is going to give us 0.061575, or 0.016, whoops, sorry, got that backwards, 0.06158 inches cubed. And because that error can be that 0.01 bigger or 0.01 smaller, the volume is also adjusted accordingly. Okay, so the volume might be 0.06158 inches cubed, a tiny bit bigger or a tiny bit smaller by that same value. Okay, so for error propagation, don't forget that you're using your change in y equation. Okay, now the next example is example 4, when we are finding differentials. Okay, so when we find a differential, because remember differentials include derivatives, we are going to find the derivative of y. So dy dx, that's Leibniz form of derivative, is equal to 2x. So to find the differential, remember differentials are dy equals. So the differential dy is equal to 2x dx. And this is really, really important because this is going to be the formatting of finding an antiderivative or an integral in the next chapter. Okay? So if y is equal to 2 sine of x, the derivative with respect to x is 2 cosine of x. So the differential is dy equals 2 cosine of x dx. Now the third one is x times cosine of x. So we are going to use our product rule here. Okay, dy dx will equal x times the derivative of cosine plus cosine times the derivative of x, which is 1. So dy dx is equal to negative x sine x plus cosine of x. And then the differential is dy equals negative x sine x plus cosine x dx. Okay, and then y equals 1 over x uses the quotient rule. So dy dx is equal to x times the derivative of 1 minus 1 times the derivative of x all over x squared, which gives us that dy dx is equal to negative 1 over x squared. Therefore, dy is equal to negative 1 over x squared dx. Very simple. And all of this is true because a differential includes the derivative. So examples 5 and 6 are exactly the same. Okay? Now, when we look at example 7, we are approximating square roots. Now, we could do the same thing that we did in Newton's method. We could say x is equal to the square root of 16.5, then square both sides, move the 16.5 over, and set it equal to y. Okay? Then we could use x minus f of x over f prime x and use Newton's method. Okay? A very close value would be, say, 4, because the square root of 16 is 4. So you might want to start with an x value of 4 and keep going until you have the number of decimal places out to 4 or 5 that are exactly the same. Okay, so what we are going to do, however, is use differentials. Okay, so I'm looking to change my color here. Okay. All right. So we are approximating the square root of 16.5 using f of x plus f prime x dx. Okay. So when you pick your x value originally, you want to make sure that you pick a value that's very close to what's under the radical. So obviously, if x is 16, the difference between 16.5 and 16 is your 0.5. Okay? Now, if we're using f of x plus f prime x dx, we are going to say that f of x is equal to the square root of x. Therefore, f prime of x is equal to 1 over 2 times the square root of x. So f of x plus f prime x dx, because we're dealing with the square root and we have x and dx under the square root, we've got f of x is equal to the square root of x and then the derivative of that. So f of x is the square root of x plus 1 over 2 times the square root of x times our dx value, which is 0.5. Now what we're going to do is go back and put a 16 in for each one of those x's. So the square root of 16 is 4 plus 1 over 2 times the square root of 16, which is 4 times 0.5, which gives us 4 plus 0.5 divided by 8. And if you put that into your calculator, 4 plus 0.5 divided by 8 is equal to 4.0625. Now, Newton's method would be more accurate. However, let's check this on our calculator. The square root of 16.5 is 4.062019.202. However, we didn't do a bad job there, okay? So using f of x plus f prime x dx does get us a very, very, very close value for the square root of 16.5. Newton's method would be better. We could get it more accurate. However, this works too. Okay, there you go. This is the last section of this chapter. Okay, so you'll have a couple of days to work on your chapter review after today's homework and then your test. Okay, see you guys. Have a good day.